All right, how's it going, everybody? We are here on Thursday, January 28th. We're going to talk about section 1.6 today with equilibria and phase lines. Um, for today's purposes, we are going to restrict our attention to only autonomous differential equations, or differential equations that are not time dependent. Um, our important thing that we know about our autonomous differential equations is that we're never going to see our solution trajectories intersect one another. And I feel like I want to talk about this ever so slightly more before I go on and read my other paragraphs out here. I would like you to kind of visualize sort of the trajectory of a from the cat. No, I'm very slow. I'm going to talk very, very slow. This is more like a casual first playthrough here. Um, is that I am going to picture the trajectory of a fly flying in front of my face, right? And what I know is that I've been 1,000 times the fly just like coming and just like landing on my forehead and me like having a freak out because there's a fly that won't leave me alone. But what I know is that that fly is located at the same point in space over and over and over again at different times, right? And at those different times, that fly is perhaps taking different trajectories through that one location in space that's right in front of my face. In that case, the trajectories that that fly is following are not autonomous. What we mean by that is there is some time dependency. Only knowing the position of the fly is not sufficient for you to know where the fly is going to be in the future, because from this position, sometimes he goes this way, sometimes he goes this way. Right? So that's different. We do have our autonomous differential equations. One of the things that we saw recently was that we're guaranteed that our trajectories will not intersect each other, and that gives us some really, really strong analysis capabilities here without actually determining any solutions. So what's so special about our autonomous differential equations? Well, the rate of change of y, dy dt, depends only on the value of y. Therefore, if the rate of change of y ever becomes zero, then the rate of change of y will remain zero for all time, because if the rate of change of y is zero, then y is stuck at whatever value it is. It's never going to change. And since the value of y doesn't change, the value of dy dt doesn't change, and so we're stuck there forever. We saw these graphically as being some horizontal lines on our solution graphs when we were looking at these things last week. So the graphs of solutions of autonomous equations will always have horizontal lines at their equilibrium solutions. Equilibrium meaning no change is occurring anymore. This makes our qualitative analysis a whole lot easier because we know that given our existence and uniqueness theorems, that we don't ever anticipate solutions to intersect one another unless some weird things are happening, like getting some situations where we don't have a continuous derivative, stuff like that. Um, but those are a little bit less common out there, right? So broadly, our goal is to analyze differential equations. Our instincts tell us that we should be doing math if we want to analyze the behavior of a solution to equation. But the theme of today's section is instead going to be, why would we do any math if we could just draw a picture and gather all the information that we wanted to know from it? Just a picture instead. And so when we talk about a phase line today, what we're saying is that there's going to be one much simpler graphical picture that we can go ahead and draw that's going to do the job for us, of helping us perform some analysis without us really doing much math at all. So today we're going to see there will be one problem in which we're going to actually do some math, and for all the rest of it, there's going to be very, very, okay, at our final fringe cases, we'll actually solve a differential equation, but that'll be our last couple examples here. So, um, and I guess the only, oh, sorry, thing right here. There we go. And I guess the only thing I want to say, as far as me writing some notes on the screen right now, is going to remember that when we're looking at our equilibrium solutions here, this is when we experience no change in our dependent variable. No change is, in calculus terms, described as having a derivative that's zero. There is no change over time. Right? So for our first example today, what we want to do is go ahead and plot a slope field, our concept from our previous lecture here, of this quadratic differential equation. And then I'm going to put in Tony stupid quotes here, simplify the drawing as much as possible. And this is one of my things where, what does it really mean when I say that? And the answer is, we're going to see that once we go ahead and draw the picture here. So the first thing that I want to identify here is that if my job is to graph this slope field, I'm recognizing that this is autonomous because there is no t dependence. If I go ahead and set dy dt equal to 0, then I can see that that's easily going to tell me that y equals 1 and 3 are equilibrium solutions. Right? So that tells me if y were to ever reach the value of 1, then dy dt would be 0, and therefore y would never change from being 1. It's 1 for all time. Same for 3. All right? So if I'm going to go ahead and attempt to graph this thing, this is telling me now that on whatever my graph looks like out here, for time and for y, I know that there should be two lines here that are located at y equals 1 and y equals 3. These are equilibrium solutions. I'm drawing them as dashed lines. They're solutions. Maybe I should be drawing them as solid lines. I just don't want there to be any confusion with my t-axis down here. And we're noticing here at y equals 1 and at y equals 3 that this kind of means things like if any solution starts between 1 and 3, it's going to be stuck between 1 and 3 for all time because this is continuous and its partial derivative with respect to y is continuous. It's another linear function that we're seeing out here. So let's talk about some other things that we're going to end up seeing out here. For example, it seems to me like if we have, and I kind of want to make a list here, if y is greater than 3, if y is bigger than 3, for example 4, I can see we're going to get positive and positive, which means dy dt is positive. So I'm going to say dy dt is greater than 0. So this tells me things like for all of our y value initial conditions above y equals 3, we should be experiencing only positive slopes in our slope field here. And as y gets bigger and bigger, that number for the slope is also going to increase, so our slope should be getting steeper. Similarly, if we look at a value between 1 and 3, then we're going to see that when we plug in a value between 1 and 3, like 2, into this equation, the first term is going to be positive. 2 minus 1 is positive, but 2 minus 3 is negative, and a positive times a negative is guaranteed to be negative here. So our dy dt here should be always less than 0 when y is in between these two. We'll also be able to see things if you wanted to do some numerical looking, like when we're really, really close to 3, we're going to get very shallow slopes because like 2.9 is going to give us only a 0.1 out of here. We're going to end up with very small quantities here. So we'll get some shallow negative slopes here, then some steeper negative slopes. And then once we get down closer to 1, we're going to get back to some shallow negative slopes here again and again. As our y values get closer and closer to 1, our first factor of our quadratic gets closer and closer to 0 right there. So we expect the overall quantity to get smaller, less steep slopes. Finally, if we go ahead and we look at some values of y that are less than 1, then what we should see here is that values of y that are less than 1 causes this guy to be negative and this guy to be negative. A negative times a negative is going to be positive, and so we'll end up with dy dt being greater than 0 again down here. And once again, I think that you can imagine that when our y values are very, very close to 1, then we're getting very small contributions from this factor, so an overall very small rate of change. As we get further and further away, these will become steeper and steeper and steeper. Another thing that you should notice as I'm drawing my last lines on our slope field here is that every single one of these rows has all the exact same slopes. That's because changing t does not affect our slope because there is no t in our slope expression. So varying the value of t did not affect our rate of change at all because there is no t in our rate of change equation. So here's really the special thing that I'm noticing. If every single one of these slope lines in each row is exactly the same as every other one in the row, then what am I really doing by drawing out all these different columns out here? And now I know this is a very rough looking sketch right here, but every single slope in this column identically matches every slope in the next column, identically matches all the slopes in the next column over. It looks like I'm literally just drawing one vertical picture and then copying my vertical picture like 8 times and calling it my overall graph. Why am I doing that? Am I really picking up any more information by continuing to go further to the right? Time doesn't change things for us. Right? Now, while my solutions still exist for all time, and we're going to be able to see things change, as you know, our solution curves are going to have 2 dimensions to them in a sense. Basically what I'm saying is I feel like we could boil this down to just saying, listen, as long as you can describe one vertical slice of this entire slope field, that is the full description of the slope field because any one vertical slice identically matches any other vertical slice. So maybe what we should do is when I say simplify this drawing as much as possible, maybe we should just be saying, let's just draw one vertical slice and be good with it. All of the information is going to be retained. Our two-dimensional picture here is just repeating a one-dimensional slice over and over and over again because this is an autonomous differential equation. So what I'm picturing here is, let's instead just draw one vertical slice. I know that at y equals 3, there is no motion, and at y equals 1, there is no motion. I'm putting circles there right now. Just hang on to that idea for a second. I know that if y is between 1 and 3, then the value of y is going to get smaller. That's exactly what we just said right here. If the value of y is between 1 and 3, then the rate of change of y is negative. And I think I can indicate this now. We're going to lose, in a sense, a little bit of information as to the different steepnesses here. But one thing I know is that all of our y values are going to decrease if they are between 1 and 3. I know that if any y value starts out bigger than 3, it's going to continue to get bigger. I know that if any y value starts out less than 1, it's also going to continue to get bigger. This seems like a pretty good description of my of everything that's happening with this differential equation right here, right? So we should notice that what we just graphed was essentially just a single y-axis. We didn't even graph a t-axis, and that kind of makes sense because where do you even see t in our differential equation? If we were to solve the differential equation, integrating would certainly introduce a t, so our solutions are being graphed in two-dimensional space. But as far as all of the classification information that I want, it can all be bound up in a one-dimensional graph rather than a two-dimensional graph, because only one of our variables is described in our differential equation rather than two of our variables being described here. Now, I left these dots or these circles as just circles sitting right here, but one of the questions that you should be asking yourself is, are both of those circles sort of serving the same role? They're both certainly equilibrium solutions, but looking at the behavior around them, is it the same business going on, or is it something different? And we'll come back to this kind of idea maybe in the second one right here. But the bottom line is, we're in a sense taking what, or maybe our good math phrase for this is sort of a projection of this slope field. A mathematical projection is when you take an n-dimensional object and represent it in fewer than n dimensions. In one case, in one sense, we're losing a bit of information here. For example, we've lost the information that this slope line is less steep than this slope line. Over here, we're just indicating they're negative slopes, and that's all we're seeing. So we're losing a little bit of information right here, which happens with any projection, right? Other projections that are out there, right? This we can see is like a cylinder. This mason jar that I'm holding right here, it's essentially a cylinder shape. But if we look at just a two-dimensional projection, this looks like a rectangle to you. And if I look at just this two-dimensional projection, it looks like just a circle. We've lost information about one of the dimensions when we look at it like down one of its axes right there, right? So that's a two-dimensional projection of a three-dimensional object, what I just showed you there. Here in this graph, this is a two-dimensional object of which we're considering a one-dimensional projection. So in one sense, a slight loss of information, but in another sense, there was a ton of repetition in our two-dimensional graph. And so we really have simplified down all of our qualitative analysis. All of our qualities are still retained right here. Where do we increase? Where do we decrease? Where do we stay the same? We can describe it fully with one phase line, which is what we call this guy here. This is a slope field to a phase line. All right. So that's one of our parts of our title today is equilibrium solutions and phase lines. Well, here we go. It looks like equilibrium solutions are really important things for us to find, particularly in autonomous differential equations, because they break up the entire plane into regions where solutions must remain, right? Between 1 and 3, below 1, above 3. Another thing that we see here is that in autonomous equations, we can always collapse our information into a single one-dimensional graph because there isn't some t descriptor happening up in our differential equation here. And this now contains all the information of a 2D graph, but it's much, much, much easier for us to make. So let's go ahead and look at another example of making a phase line. And basically the bottom line is, like, I'm hoping that you're looking at this picture and being like, dang, I hope I don't have to interpret any Tony's slope fields ever again. This picture kind of sucks right here. This phase line, a lot easier for us to interpret. And maybe one more statement right here. This phase line allows me to make really simple statements about long-term behavior. Now, if you ask me questions like, discuss the long-term behavior of any initial condition that starts at y of 0 equals 2. Well, that starts right there, y of 0 equals 2, and I can see it's going to go down until it hits y equals 1. There we go. I know about my long-term behavior. I can identify the long-term behavior of any initial condition by just looking at the arrows associated with that segment of the graph. Really, really easy for us to do our analysis with a nice one-dimensional graph. This is basically a number line with arrows on it. Not going to get a lot easier than that. Let's look at another example here. Now that we know what a phase line is, let's just say, let's skip over the slope field part and just talk about the phase line right here. So what I want to first do is find our equilibrium solutions. I know those are really relevant breakdown locations on our phase line graph here. So what I want to do is find where sine of y is equal to 0. We've all taken trig. We know that sine is 0. Sine is measuring our height on the unit circle. So sine of y is 0 when y is 0, when y is pi, 2 pi, 3 pi, 4 pi, right? All of our integer multiples of pi seems to be when this is happening. So y equals pi k, where k is an element of the integers, is our equilibrium solutions. So notice here, there is an infinite number of equilibrium solutions, which isn't too crazy. This is literally just the same thing as me saying the equation y equals sine of x has an infinite number of roots, x-axis intersections. It's essentially an equivalent statement right here. I just set sine of y equal to 0 and went ahead to solve here. So what should our phase line look like? Well, picturing my phase line here, and again, these are my y values, and I want to know how y changes. Well, I'm going to go ahead and at least mark my y equals 0 here. And then I know that there should be some more here, like at y equals pi, at y equals 2 pi, etc., right? We can go in both directions here and get all of our integer values. One thing that I almost just did on my graph that I'm glad that I managed to resist the temptation is, in general, if I were to say to you, hey, go ahead and draw this number line, a very typical thing to do on every number line is to put arrows on both ends indicating that that line goes on forever. Notice that we're using arrows for a different purpose here, so I don't want to just like put an arrow indicating that this is an axis that goes on forever. All of my arrows are going to indicate motion, like a change in our y value, rather than a description of the line, but a description of the quantity instead, right? So one thing I've done on my phase line is I've graphed where I know a bunch of my equilibrium solutions are, and instead of maybe putting that arrow, maybe we just like do something like that to indicate that those equilibrium are going to continue to occur out there. My next question is, how do I plot some arrows on this thing? How do I indicate my direction of motion? Well, let's just do a couple quick easy ones. If our y value is between 0 and pi, then our rate of change of y is the sine of a angle between 0 and pi. And I know that for any angle between 0 and pi, the sine of y is positive because we're above where we always have positive y values there. So it seems like the rate of change of y is positive whenever y is between 0 and pi. That leads me to believe that it's reasonable for me to place some upward arrows here. But what I know is that once we progress y through pi, right, there's y at pi right there, once we go past that, now sine of y is negative, which means the rate of change of y is now negative. That means our y values are decreasing if we're between pi and 2 pi. All right, so now that means I know I can draw some downward arrows here. Once we pass back through 2 pi, now we're getting back up between 2 pi and 3 pi. We're back to positive signs, positive sine of y, and therefore positive rate of change again. So I can get some more upward arrows here, right? And it looks like we're going to get that similar action going on out here. We know that sine of y has a period of every 2 pi, so it is the case that I expect my phase line to be identical every 2 pi interval right there for that to keep repeating because sine has that period of 2 pi. So there we go. We got a phase line here. And again, we can see what our long-term behavior now is. Now I can say things like, oh, y has an initial value of 3 pi halves. What's the long-term behavior? Oh, you started at 3 pi halves. It looks like you're going to decay down to pi in the long run. That's what I know is going to happen. I can see a qualitative analysis of any initial condition associated with this differential equation without ever solving it, without ever actually plotting any of its true solutions. Just looking at a one-dimensional phase line gives me a full description of all long-term behaviors of all initial conditions. That's really easy. So this is the reason why identifying these equilibrium solutions matters. This is why it really matters that we know that solutions can't cross over one another from our existence and uniqueness theorems. It helps us make very large statements with very little bit of information here from our differential equations. So this is our qualitative analysis. We're not analyzing the qualities of the graph. It's not a quantitative thing. I'm not finding something like, oh, the slope is -6 when y is 4. Like, I don't have any information like that, right? It's not numerical information. But we can see the broad strokes of what's happening very easily. Nice one-dimensional graph. Didn't even do any math really to get there. I just quoted some known statements from trigonometry right there. All right, pretty nice and easy. So Again, I'm slightly dissatisfied with the fact that I keep on labeling all of our equilibria the exact same when they seem to be doing slightly different roles as one another here. So my next question is here, like, based on our last two examples, what can we say will happen to any initial condition associated with an autonomous differential equation? And what we can see from our last two examples is this. Here, I see initial conditions that started above 3 tend to positive infinity. Initial conditions that are at 3 stayed at 3. Initial conditions between 1 and 3 went to the equilibrium at 1. Initial conditions below 1 went to the equilibrium at 1. So it seems like in that graph, every single initial condition either remained in place because it was at an equilibrium, it tended off towards infinity because it was increasing or decreasing with no other equilibrium to block it, or it tended towards an equilibrium that it wasn't currently at. It was in between two of them and it went to one of them. Down here, I can see some similar behavior. I can see that any initial condition, for example, between pi and 2 pi, will tend down towards the value of y being pi. Anything between 0 and pi is going to increase towards pi. And it looks like here, because there's an infinite number of equilibrium in this case here, it looks like there's never going to be a y value that's going to tend off towards infinity, but we still did cover two of the three cases we saw above. Either you started at an equilibrium and stayed there, or you started between two equilibrium and you tended towards one of them. So it looks like kind of we can make this general statement here, like if we start at an equilibrium, we stay there forever. Otherwise, we tend towards an equilibrium or towards plus or minus infinity. Yeah, the clickety-clacks going on over here for sure. So that's everything that can happen, right? So another nice thing to know in autonomous scenarios here, autonomous single differential equations, is every single solution that we get is either going to tend towards positive or negative infinity, or it's going to tend towards an equilibrium if it's not already at the equilibrium that's sitting right there, okay? And that's good. Like, that means that there's very, very few things that can happen, right? So now I've complained enough about my open circles all being the same, even though I don't quite think they should be. Let's look at example 3 here and see how we want to distinguish between what I believe are the two different types of equilibrium I'm seeing here. And then we'll ask, are there only two types of equilibrium that we can experience? So let's look at this kind of from like a different perspective here. In this case here, I'm not actually telling you what the differential equation is. Instead of telling you like a function that f of y is, I'm just saying, I don't know, but there's its graph. Now, obviously, in this case, the graph looks like a parabola, and we could therefore, in a sense, come up with an equation. But I did a really important thing here, which is that I literally just labeled nothing. Right? There's not a quantity for us to know out here. All you know is that this is the graph of y versus dy dt. So I can at least label y and dy dt here. And I don't know what these points are, but I'm just going to label them the most generic thing that I can, just A and B, just so that we can at least like talk about them. And here's the reason why I think those points are important. Notice that in the graph of y, dy dt, the roots of the graph that occurred at y equals a and y equals b, those are exactly where dy dt is equal to 0. It looks like we have equilibria at y equals 0, right? Or sorry, equilibria at y equals a and at y equals b, because those are the two locations where the vertical height of this graph is 0, but here vertical height is actually measuring the rate of change. And so the rate of change is 0 when y is a or when y is b. Let's try and make some other kind of more verbal statements like we did in our first example here. So if y is less than a, if y is less than a, so that means that we're interested in this left region of the graph over here. It looks like dy dt is greater than 0. It looks like if y is equal to a, dy dt is equal to 0. It looks like if A is less than Y is less than B, if we're stuck in between those two, notice that if our Y value is in between A and B, then our rate of change of Y is negative, right? dy dt has a negative measurement here. And if Y is equal to B, we know that dy dt is 0. That's one of our equilibria that we've already identified. And finally, if Y is greater than B, we can again see that when the Y value is bigger than B, that our dy dt is a positive value out there. I don't care about what the number is. I just am really looking for the sign, positive or negative here. So notice that this right here is just our really long form way of describing a phase line, right? This is Y right here. Then I'm just going to mark, I want to be careful here. I'm going to mark a circle at this equilibrium. I'm going to mark a circle at this equilibrium. I know that our change should be positive if these Y values are, so the reason I'm pausing right now is I just realized I organized some things a little bit differently. Then I think I want to kind of flip this graph, and here's why. A is smaller than B, but the way that I wrote this stuff in order here, I have that A is on top and B is on bottom. But if I'm drawing this vertically, I kind of want my larger quantities on top and my smaller quantities on bottom. So I think I want to, like, I know this is kind of ridiculous, but I do kind of want to flip this stuff right here. Oh, come on, you can do it, pen. You got it here. No, am I not allowed anymore? Come on, man. Oh my gosh, it's clearly not what I have selected. You're on the eraser. Erase. There we go. I want to just flip this just because I want to keep my, I want my, like, expressions to match my graph right there instead of one be a vertically flipped version of the other. I can even leave my phase line right there. So all I'm saying right here is I want to start on the big end of things. If Y is greater than B, big on top, small on bottom. That's all I'm doing. Then dy dt is greater than 0. Y equals B. Dy, yeah, consistency is the hallmark of a champion. Always do things the same so that you're not tricking yourself. Dy dt is less than 0. Y equals A. Dy dt equals 0. And finally, if Y is less than A, if it's lower than our lowest quantity of interest, oh my gosh, apparently I can't draw A's today either. Apparently there's zeros with sticks on them. Here we go. Then our dy dt, when Y is less than A, is positive. Okay, now I'm just going to use these expressions to directly interpret them as my phase line, right? Equilibrium, circle. Equilibrium, circle. Above this equilibrium point, our Y value is getting bigger, and therefore I'm going to place some up arrows on there. In between our two equilibrium, our Y values are getting smaller, so I'm going to place some point and down arrows. Below Y equals A, our Y values are increasing. So I'll place some up arrows there. So now let's finally answer this question. What's the difference between these two equilibria? What different jobs are they actually doing right there? All right, and here's one of the things that I'm seeing. Points near this equilibria move away from it, whereas points near this equilibrium move towards it. They kind of have the opposite behavior with surrounding initial conditions. If you started very, very near to one of those equilibria, you have opposite, yeah. So one exerts and one attracts. We're going to use words very, very, very similar to those things, synonyms of those guys right there. Here, we're going to say that Y equals B is a source because things grow out from it. And we are going to classify Y equals A. Oh, apparently I'm getting too excited. I can't write my words anymore here. Y equals A is a sink. And these are pretty typical words used to describe these types of equilibrium. Visually, we want a visual indicator of what's going on right here, and it is typically the case that we fill in the circle associated with sinks to indicate that we do like kind of get there, whereas we're leaving the source, and so it is sort of an empty circle right there. Now, so very good question. The question in chat is source, meaning things are created from that point. Importantly, recognize that if we start at Y equals B, we never leave Y equals B. If you start at Y equals B, you will remain there for all time because the change in Y is 0. So things aren't coming out of the point Y equals B. But points that begin in some region around equals b will move away from y equals b. But it's important to make that distinction that at b, there's no motion ever. Things don't come out of y equals b, but near y equals b, they move away from y equals b. So again, and again, if some change were to happen to where you would be at y equals b, and then off of y equals b, you would move away forever. So here's my example to you. I think what we should sort of picture here. Okay, we're going to give a couple of different names to these actually right here. And so let me write some things, and then I'm going to give a different analogy that I think will kind of help us visualize what we really mean by sink and source and by what's really happening at A and at B right here. So I'm going to say y, get out of here, capital Y. Y equals B is a source of all solutions near but not at B tend, wait a minute, what am I writing here? Whatever. Tend away from y equals b as time tends towards infinity. Oh, come on. Y equals a is a sink if solutions, all solutions near A tend towards y equals A as t approaches. All right, so this is just saying if the long-term behavior of your solution is towards or away some point, then we classify that as being a sink or as being a source here. And I think a good thing to kind of help visualize with this. Yeah, and there we go. And so another good reason right there why there can't really be any solution crossing y equals b and y equals a right there. If you get to that equilibrium, you will have to stay at that equilibrium. So a thing that I like to picture here is a hill and a valley. And you should be picturing a ball sitting in the valley and a ball on top of the hill right there. Right? So here's the deal. Technically speaking, both of those balls are perfectly at rest. The ball on the top of the hill is located at the exact perfect location where it's not rolling down either side. The ball at the bottom of the valley is just at rest at the bottom of the valley. It's rolled down there and it's at the lowest point in the valley. Now, what's going to happen is we want to consider what happens if this system is, and here's our math word, perturbed. A small perturbation in the system. What that means, according to my hill and valley scenario, is I'm going to come over here and I'm going to bang on my desk once really, really hard. What's going to happen to both of those balls? They're both currently at equilibrium. When I bang on my desk really hard in that physical system right there, what I expect to see happen is this ball that's currently at equilibrium on top of the hill is when I bang on the desk, it's going to roll to one side. And the question is, will it ever go back to being on top of the hill? And the answer is no. It's tending away from the hill for sure. On the other hand, the ball that's at the bottom of the valley, when I bang on my desk really hard, it might roll a smidge up one of the two sides of the hill, but then what's it going to do? It's going to go right back down to that bottom of the valley right there. So another way that we describe these guys is as being stable equilibria versus being unstable equilibria. What this means to me is, technically speaking, if you start at y equals b, you'll stay at b. But all I have to do is come by and bang on the desk once, and once you've fallen away from b, you're going to leave b forever and never come back. That's unstable. On the other hand, y equals a we would refer to as a stable equilibrium, because if you start at y equals a, you'll stay there for all time. If I were to come by and change the system by banging on the desk, you're going to fall off of a little bit, but then you're going to go right back towards it again. So our solutions are stable near it. They don't just fall away, as we see from the top of the hill to the bottom of the valley. Our other kind of analogies that go exactly with this are, imagine the two ways that a quarter can be stable is one if it's lying flat and one if it's vertical. Those are both equilibria, but we know that if a quarter is flat and you bang on the table, it might jump a little bit and then it will go back to being flat, back to where it was. On the other hand, if a quarter is vertical and I bang on the table, it's going to fall flat. It's never going to go back to being vertical. So this would be our unstable equilibria for a quarter, and this would be our stable equilibria for a quarter. Final example is think about a pendulum that's on a fixed rod, not a string, but like a metal wire between it. We know that if we have an equilibria or a pendulum, that things are going to swing back and forth and come down to a stable equilibrium that is vertically pointing down. If I were to perturb the system, things just swing back to being down again. So this is not just an equilibrium, it's a stable equilibrium. On the other hand, since this is a rigid object, there's technically got to be a perfectly vertical orientation that a pendulum could technically be at right here. Where technically, if it's here, it's going to stay here. It doesn't have force going left or right to make it slide. But all I've got to do is come by and bang on the table again, and we know that that thing's going to swing away and tend towards a more stable equilibrium over time right there, right? So these are a bunch of physical interpretations that we can give to this idea of sink or source. Stable or unstable equilibrium right there. Some equilibrium solutions, and again, picturing this as an equilibrium for a pendulum is a little bit odd, but I think you all agree that, and I mean, isn't this like the game that you play with things like this? It's like, let's see if I can get it to stand up just right kind of thing. It's like getting to an equilibrium where things don't move anymore. But you know, it takes the tiniest of nudges for it to move away from that positioning forever, right there. And it will never naturally go back to being in that position. So making this distinction between things that we move towards and things that we move away from are important. But again, notice I keep on mentioning this perturbation. This would stay like this forever if we never experienced any external forces altering the system that we're discussing, right? It took the bang on the desk for us to rotate away from this right there. We changed the system. So solutions aren't coming out of this unstable equilibrium. This unstable equilibrium stays at equilibrium for all of infinite time as long as the system is never altered, right? Now, initial conditions very nearby, but not the same as that one, will tend away, right? If I started my pendulum right here, you guys know that as soon as this system is allowed to do whatever it wants, it's going to do that guy right there, right? So this was a nearby initial condition. It wasn't vertical. It was slightly angled right there. This is a near to an equilibrium, and we moved away from it. That's why it's a source or an unstable equilibrium right there. So those two names, I think that we've got these really good visualizations right there. And so for a pendulum, let's just draw this one as well right here, is that we've got a unstable equilibrium and a stable. Right. One, if you perturb it, you'll go back to it. The other, if you perturb it, you'll go away from it forever. And I think that these two kind of physical scenarios are great, great, great descriptors of these things that I'm seeing right here. All right. So, more generally, how should we classify any equilibria? Are the above two cases the only possible thing, just a sink or just a source? Or are there other things that we might end up experiencing out there as well? Hopefully you believe that because I'm asking that question that there are some other possibilities right here. And here's what I kind of want to, oh, sorry. I moved on a little bit. I want to come back to our previous example and look a little bit more at this graph. Another thing I think that's really valuable for you guys to notice is that literally this is a y-axis with the values of A and B labeled on it. Just like this is a y-axis with the values of A and B labeled on it, we can literally just put these arrows in their exact same locations and orientations on this axis, and that is the phase line, right? dy dt is positive right here, so our y value increases. dy dt is negative right here, so our y value decreases. dy dt is positive out here, it increases. This is the phase line. I just literally copied it on the y dy dt graph right there. That is the phase line. It's literally just rotated right there. There's no difference that we're seeing, right? So that's a valuable thing for us to kind of see here. And now I'm seeing something that's maybe an additional feature that can help me describe what's going on. I'm noticing here that this line passes through the y-axis, and again, when I say y-axis, in this case, I mean horizontal axis. I know that when I say y-axis, all of you guys are visualizing this because that's usually our x and y-axis. That's a little different right here, right? So the y-axis, our horizontal axis, as our dy dt curve goes through it right here, it seems like if our dy dt curve has negative slope, then it's a sink. And if it has positive slope, it's a source, because positive slope meaning it was below it to the left, so our arrows are to the left, and it was above it to the right, so our arrows are to the right. We can kind of use this type of visualization to help us out with our classification. Right? So we say here, type out a little bit more here. Right, so we always want to know about these roots of f of y and what happens as we pass through them here, right? So I'm going to draw some really generic scenarios here for us, a bunch of them. So one thing that might happen in our y dy dt graph is that we might have some solution curve that passes through this point of y equals a right here. And in this case, what we can see is that our dy dt is negative when y is less than a, and it's positive when it's greater than a. So it looks like we are experiencing a source type behavior here because solutions are moving away from the equilibrium at y equals a. So here y equals a is a source. And the thing that I'm noticing right here is that f of y, that's our f of y curve right there, the slope of f of y is positive. And that's kind of the thing that's making us a source. The slope through the root was positive, and that resulted in the curve being below the root to the left and above the root to the right. And that gave us the arrows that qualified this thing as a source right here. So what I'm noticing here is that the slope of f of y is positive, and that seems to be linked to being a source. Ooh, sorry. I should say, I want to say here, f prime of a at the location. Their slope might be positive, negative at different places in time. I care about what was the slope through the root right there, and it was positive near the root. Okay, so there's one situation right there. The other situation that we've already seen is, I don't want to draw an F right there. The other situation that we want to see, that we've already seen, is that in our y dy dt graph, that it might be the case that we have some solution curve that passes, sorry, not a solution curve, but a function, our f of y function here, that might have negative slope as it passes through a equilibrium that's at a. Again, notice here, dy dt is positive when y is less than a, so it looks like this solution should be increasing, right? Positive values for dy dt means y is getting bigger, so I'm drawing arrows to the right. Over here, dy dt values are negative, and so y is getting smaller, and so I'm drawing arrows over here to the left. It seems here that y equals a is a sink. And further, I can see that the slope of our graph through the origin right here is going to be negative. So this should lead us now to think about what our other potential cases might be. It seems like our classification of sink and source is directly tied to the slope of f of y at the equilibrium a being, so far, greater than 0 or less than 0. And so what's our other scenario? Well, it could be equal to 0 right there, right? So what does it look like if we have an equilibrium where we hit an axis, but the slope is 0 at that axis? Well, there's a couple things that we might want to consider here. And so I'm going to kind of draw a dividing line here because these other cases are going to closely relate to each other. Here's one way that I think that this could happen. Right? Maybe we have something like, a y plus 2 squared as our dy dt function right there. We know this graph will have a tangent root, in this case at y equals negative 2. I'm not trying to bring numbers into this too much. I'm still just going to label this a instead of negative 2 right there. But the point is here, we should be noticing that in this graph right here, it seems like dy dt is positive always. So our y value always gets bigger. So it looks like in this case, y values that start out less than a will increase until they get to a, and then they'll stay there. And then they just won't go anywhere. If I were to come along and bang on the table really hard when you're sitting at y equals a, if you fall below a, you'll go back to a, so that's stable. But if you were to fall above a, you would tend off towards positive infinity forever, and that's unstable. So it seems like this guy is sort of half stable and half unstable, right? It seems like there is a, if we're drawing our phase line for this guy, it seems like when we're at y equals a, if we start below it, we increase. If we start above it, we increase. So typically, this is drawn with a half filled in circle right here, and we refer to this y equals a as a node. And in this case right here, we do have that f prime of a is equal to 0. And so now you should ask yourself, are we always going to get nodes when the derivative is equal to 0? And well, not quite. There's other things that could happen when we have a slope of 0 at the origin. Now maybe consider for yourself the equation, maybe y cubed. Well, I know that if you were to take the so we're going to talk about one of these physical systems right here. There's some interesting things that happen sort of biologically with this. So one of the things is, the question is, what kind of physical system could this represent? And that's a good question because I think we can kind of see the physical system thing that could be represented here. Here we are at the top of a hill. Here we're at the bottom of a valley. But what's going on with this? This is a little bit more complicated, but here's an idea that I think that a lot of us can get on board with. In our bodies, biologically, there's lots of processes that our body will start if a hormone level gets high enough. And so what that means to me is if I were to decrease my hormone levels, nothing really is happening differently in my body than what they were. And if I were to increase them a little bit, maybe nothing would change. But if I increase them enough to get over some threshold, then our body's going to sort of turn on some process that it's now doing. Things like puberty and other weird things that our bodies do with a billion different chemicals that are in our body now. What could happen is I could turn that hormone back down again, and it would not turn puberty back off. It's already been turned on. The flip has been switched. So we sort of did this like falling off of a ledge by going over the equilibrium point right there, and it is now going to tend off in some direction regardless of whether or not our input of that chemical is still at a high level that's up there. This is something that we're going to look at again a little bit later. But you're asking the right question. We do want to think about what kind of like physical systems that we could see here. And there's some sense that which we typically kind of like separate theory from application a little bit. And that's a little bit what's happening today, a little bit more of the theory side, which is why we're talking about derivatives of of differential equations and stuff like that. But yeah, we are going to talk about some physical systems of when do we see this type of behavior, or what we should be saying is if we create a model that has this behavior, maybe what we end up deciding is that there aren't physical systems that look like this, and consequently, if we build a model that has those features, that might be a red flag to us that that wasn't actually a good model to model a real world physical system. So there's kind of this thing that says sometimes you just try to build a model and then you realize that it has features that aren't really representative of real world things, and therefore you maybe want to change the structure of the model that you've built right there. No, and you're good right there. It's good to be thinking about these things. We're obviously not doing math for math's sake here. We're doing this because this is supposed to be modeling real world phenomena. But obviously, as it goes with math, we want to kind of fill in all the little nooks and crannies to ask, like, what are all the potential scenarios that could happen out here? And that's kind of all we're filling out right now. So back to our y cubed right here. One of the weird things about y cubed that you guys know is that the function y cubed doesn't have any maximums or minimums in it, right? But if you were to take the derivative of y cubed at 0, it's 0. What I know is that whenever I draw y cubed, I always accidentally draw the graph of tangent, which has a slope of 1 through the origin. But I know that y cubed is a slope of 0 through the origin, so it should be a little bit more like I kind of did a close job right there. Okay, if I make my dot big enough, there we go. The slope is 0 at the origin right there. I'm still going to call that a for our general label right there. But in this case, you should notice that even though the slope is 0 right there, I am still seeing that here our y values are decreasing, here our y values are increasing, and so this guy looks like a source to me. But we had that f prime of a here was 0, but we got a source. And similarly, we could picture negative y cubed. Let me try that again. I could try to graph negative y cubed. There we go. There's a much better y cubed graph right there. And here what we can see is that here dy dt is positive over here, meaning it's pointing inward, pointing to the right. Here, dy dt is negative, so it's pointing to the left. Y values are pointing to the left. This looks like a sink. So the bottom line here is we can't really trust what's happening if we find that f prime of a is equal to 0. It seems that if f prime of a is equal to 0, we could see any of a number of different type of behaviors. But if we find that f prime of a is positive or negative, that's immediately going to tell us, are we growing away from it, positive, or are we decaying towards it, negative, a sink right there. So I do think that there's a nice tie to this. This says to me our rate of change is growing, so it's a source. Our rate of change is decaying, so it's a sink right there. But again, the bottom line with what we just walked through right here is we can't classify f prime of a equals 0. Right? This is our takeaway from this third grouping over here. So if we want to classify it as an equilibrium as a sink or a source, it looks like what we could do is we could take the derivative of the function associated with our differential equation, we could plug in the equilibrium location, and we could find out if it's positive, negative, or 0. If it's positive, we'll conclude it's a source. If it's negative, we'll conclude it's a sink. If it's 0, we apparently have to do some more work to conclude, because what we've seen in just these easy algebra examples, a quadratic and 2 cubics, that it could be any type of behavior if we find that our derivative of our differential equation expression is 0 at that equilibrium location. So this just says no information if you find that f prime of a is equal to 0. So now let's actually go ahead and do this, and let's look at a gnarly differential equation that we otherwise might struggle to analyze, right? So in example 4, I'm saying to you, I can look at this gross equation right here, and I can at least see that this is, y times some big old nasty thing that's out there. So I know that I have a factor of y and a factor of the big old nasty thing. If either of the factors is equal to 0, then dy dt equals 0. So we can easily see that y equals 0 causes dy dt to be equal to 0. So y equals 0 is an equilibrium. Right? That's kind of easy to see just by a little bit of algebra concept right there. Y equals 0 makes dy dt equals 0. So I know it is an equilibrium. My question is, can we classify it? Do you know if it's a sink or a source or a node? So this collectively is what we are calling f of y. And what we've just learned is if we take the derivative of f of y and plug in our equilibrium point, if we get a positive, we'll call it a source, and if we get a negative, we'll call it a sink. So let's go ahead and see if we can do that here. Certainly, this is going to be a gross derivative. Part of the reason this is going to be gross is because this requires a product rule, right? I've got a product of two functions of y. So for f prime of y, I'm going to take the derivative of y, that's 1. I'm going to leave the other parts alone. Plus, I'm going to take leave y alone, and I'm going to take the derivative of this inside part right here. Right? So the derivative of this inside part, well, maybe I'm just going to call this the derivative with respect to y of our cosine term. I'm writing some shorthand right here just to get away with my oh, I can give myself a smidge more room here. Maybe I can do that. Nope, I'm still going to dot this guy for right now. What I know I'm going to do is I'm going to plug in y equals 0 into this thing right here. And so notice, let's see here, f prime of 0. Well, when I plug in 0 here, I'm going to get the cosine of 0 in this expression. I'm going to get minus 0, because that's 27 pi y to the 4th. Right? I'm going to get plus. And here's the thing I'm noticing. I don't even really care what I get out of this derivative term, because I'm going to get 0 times that derivative with respect to y of the cosine stuff minus the 27 pi y to the 4th, or pi times 0 to the 4th. The whole point is I'm going to get 0 times everything right here. So it looks like when I compute f prime of 0 in the laziest way possible, I'm getting 1 times 1 plus 0 times something. I don't care what the something is because it's being multiplied by 0. and therefore f prime of 0 appears to be 1, the laziest evaluation I could ever do. And since I found f prime evaluated at my equilibrium location to be greater than 0, positive, it seems that we can conclude that it's a source. I think solutions will be moving away from y equals 0 on this graph. And notice how terrible, I mean, just think of how terrible this is to analyze generally, right? If I'm going to try and solve this, no way. You can't do that calculus. It's tough to talk about this. Draw a phase line for this? I don't even think I can do that. It's really, really, really hard to find our other equilibria that may or may not be associated with this guy. So, super good question. So the question here is, didn't we already have f prime? What I'm defining f to be is what the derivative of y is. So dy dt, I'm saying is equal to some f of y expression. So in this case, f of y was like y cubed or y plus 2 squared. And that is the derivative of y. We're now taking an additional derivative of y because I'm seeing that this graph right here, this is the graph of f, where f is the same thing as dy dt. I'm taking sort of another derivative. So this is really like the second derivative of y. That seems to be our decider right here. So I maybe could say here, this is y double prime of a is greater than 0, or y double prime of a is less than 0. But that's just because we're taking a derivative of a pre-existing derivative that we're looking at right there. And so I think the weird thing about this is just that dy dt is an axis on this graph. So when I say dy dt, that's literally the height of the graph, not the slope of the graph. The derivative of dy dt is the slope of the graph in this case. We're already one derivative deep. We're looking at the slope of the curve, where the curve is already a derivative function. So it's actually the second derivative of y right there. And that question that you're asking right there, it's like, in a sense, it's like a simple explanation for me to give right there. That is one of the most common mistakes to make in interpreting these things. And we're going to see we have a lot of different graphs. And it is weird to graph a derivative graph and then talk about its derivative. So that's, in a sense, like a simple question to answer, but an incredibly common mistake that does get made in a lot of this analysis here. So you are not alone. The fact that you are the only one that asked that is just because you're the one asking it in chat right now. A lot of people are going to make that little mistake here for sure. So that's a good question right there. It's a very, very common thing for us to have to kind of deal with right there. So thank you for asking that one right there. So what I want to do real quick before I walk away from this problem is, I've just been yelling at you guys for a long time here. Let's go take a look at the graph of this thing. Let's have something else plot a solution curve for us here so that we can feel a little bit better about what we're seeing right here. We believe that y equals 0 is an equilibrium solution in an autonomous differential equation, meaning whatever the graph of this thing looks like, might be easy, might be crazy, I do expect a horizontal line solution at y equals 0. And because of this math that we just did over here, I think that solutions near it are going to move away from it. We just determined that it's a source. So that's what I'm expecting to see graphically to feel good about the math that I just did right here. So let's pop over to our solution grapher here. I kind of decided I like this one bluffed in enough to use it right here. So I'm going to type in this horrendous differential equation into this thing right here. And let's see what we get. So our equation here is y times, oh man, where's this nasty boy here? Cosine of y to the 5th plus 2y minus 27 pi y to the 4th, close my parenthesis, and here's the thing I'm seeing here. And what I can see is sorry. Okay. I was like, oh, they're going in towards it. Nope. So notice here, our bounds are going from -3 to 3, but the action that I'm interested in is very much like at the center of this thing. I'm going to make this just go from -1 to 1 to kind of hone in on specifically the behavior that I'm actually interested in. And now we can see what's happening here. Y equals 0 does, So I'm going to do this. 0, 0, and submit. And what is incredible, oh, actually it looks kind of okay right here. If you can see this, maybe you can. It did just place a perfectly horizontal green line on the x-axis right there to say that y equals 0 is a solution. And what I can see is when I click near it, our solutions are moving away from it. So this totally agrees with the things that we just said, which is that that y equals 0 is a source, meaning that initial conditions near it will move away from it. It's sourcing out from it right there. Now, some other interesting behavior that we weren't able to see by looking at this thing algebraically is it looks like there's other equilibrium solutions right here, right? It looks like there's something at like y equals in the ballpark of like 1/3 or something like that. Now, since there's a cosine function involved, I'm much more likely to believe that this isn't like 1/3, but maybe something like pi sixths or pi twelfths or something, some fraction of pi that's out there, right? But it does look like there are two other equilibrium solutions here that are symmetric on either side of 0. But man, if you can solve that equation, then good on you. I don't think I can. And it's not what I was just technically asking about in this question right here, but we verified what we saw, the easy parts. Y equals 0 is an equilibrium. Solutions move away from it as time increases. That's exactly what we were able to do without a graph right here, which is somewhat satisfying right there. Right? So double checking the math that we do with a graph, or double checking a graph that we did with some math, always good multiple perspective things to be able to do here. So never forget that things are going to make these graphs for you, and that you should be able to use these, trust these. Sorry, I just have a dangerous thing there. Maybe you shouldn't trust these all the time. We're absolutely going to see some scenarios later where we get, in a sense, some incorrect graphs here, but that's all the stuff we're going to talk about in our numerical unit of when do our numerical approximations give us misleading results. But that's going to be more about our systems of equations. We'll get there eventually. Don't worry about that guy for right now. As far as I can tell right now, this graph completely agrees with the math that we just did a second ago here. Okay, so let's look at just a couple more things right here. I want to return to our population model for our last kind of regular example here, and then I just want to talk about two fringe cases of some screwy behavior that can happen here. We've seen some really like nice clean things, and even with how not clean this equation is, we still were able to like do some clean predicting with what's going to happen, talk about long-term behavior of initial conditions near y equals 0, stuff like that. Sometimes some weirder stuff happens, but we'll talk about that in a second. Let's return to our population model. We started this class, the first differential equation that you guys saw, dp dt equals kp right here. We referred to this as our unlimited growth model. The problem with this model is it just says that populations are just going to get bigger forever, right? This says if you start at a population of 1, you are going to grow without bound for all time. And I have some pretty major issues with that sentence I just said right there. You should think about what are your 2 issues with that sentence. One of the issues that we have with that sentence is there are no biological populations whatsoever, even humans, as we're finding out right now and over the next 50 years, that can ever experience unlimited growth. There's always, in every natural ecosystem, an upper bound that we're calling N, our carrying capacity, that is ultimately saying there are no more resources for more members of that population. This is the largest the population could ever get relative to the amount of resources that we currently have. So here we say N is our carrying capacity. It's sort of our, and I'll put this in quotes, it's our natural maximum. This says you can't naturally, organically get above that many members of a population. There just isn't enough resources in that population's environment to sustain that. If you ended up somehow having more than that, then you should more likely expect for our population to decay back down to that carrying capacity that we're seeing right there. Now my question is, what's still not quite right about this model? What update do we still want to make this more reflective of how populations actually change over time? The sentence that I said 1 second ago in our first model scenario here was that this says to me, even if we start with a population of 1, we should expect it to grow without bound for all time. We fixed the grow without bound for all time by limiting the growth to a maxing out at this carrying capacity. But the other major issue you should have with what I just said is, if we really have a population of 1, is it really going to grow? And most things on Earth, if we're talking at least about like most mammal species and stuff, they perform sexual reproduction. It requires 2 to make another 1, right? So when we get down to having the last member of a species, there's a special name for this. I can't remember what it is, but there's some outrageously depressing name that's associated with the very last known member of a species, usually living its life in a freaking zoo. We're going to experience a ton of that in our lifetimes here. That's sad. But the point is this. It takes more than one to grow a population. And in fact, we know it takes even more than two or three or four or five or even 100 to grow a population. Like, you know, we're thinking to ourselves, I use my like depressing example of like African white rhinos, which I think are down to like uh, none or one or 15 or something like that in the wild. Um, an endling. Oh, thank you for looking up our depressing facts, everybody in chat. An endling is the last member of a species. How incredibly depressing. If you're not sad enough today, just go to Wikipedia and look up endlings. Um, but even still, even if you're not the endling of a species, I mean, picture the African white rhino population. If there's 100 of them in nature, do we really think that they are going to encounter each other often enough to produce enough young to grow the population into an actual viable population? We know the answer is no. A lot of things that we've learned biologically speaking is that genetically we need a lot of variety in our population to make sure that we're not at risk of being heavily affected by small changes in our environment, right? So if everybody's very, very closely related to one another, has exactly the same genetic traits, that makes it very, very difficult for us to survive difficult things in the future because one virus, one drought season, one cold winter, one algae that grows on your tusks, whatever it is going to, all it takes is that to affect one person in your population. If all the genetics are the same, then it affects everybody in the population. You get wiped out. There's currently some major concerns. Cheetahs are a species that we know are all almost genetically identical to one another. They have a shockingly low amount of variance in their genomes. So that means that they're highly susceptible to their entire population being wiped out by like one weird thing happening. Whereas in lots of other populations, there's lots of diversity within the population. Super cold winter happens, doesn't kill off everything. The ones with the hairier coats survive to make the next generation that are more likely then to survive the next very cold winter, stuff like that, right? So the bottom line here is what I'm saying to you is for most mammals at least, in fact, for most macroscopic organisms, a population of even 100 actually should be suggesting a declining population, not a growing population out there. Uh, so kind of what we want to do is we want to update our model. Let's get a third model here. And what we want to do is we want to introduce a concept like our carrying capacity, but it should be going in the other direction, right? Here we said that we wanted to be experiencing a negative component if our p-value was larger than our n value. If our population got bigger than our carrying capacity, we wanted this term to go negative. However, if our population is smaller than something like a minimum viable population, let's define that. M equals minimum viable population. When I say viable, I mean it still has the potential to be a sustainable population. 100 African white rhinos is not a viable population. It's guaranteed to tend towards extinction without like an outrageous amount of like human intervention, right? So minimum naturally viable population size. It's sort of the opposite of a carrying capacity. You gotta have at least a good handful of them to repopulate right there. So I'm going to call that capital M to be associated with our capital N of our carrying capacity right there. And the thing that I'm thinking is that our third model should be like building off of our old model. What I mean by that is I'm saying I still want to experience exponential growth with moderate sized populations. I still want our population change to be negative if our population gets above our carrying capacity. But now I want to include a third factor, which I'll just call something, which should cause us to again have a negative contribution if our population is below a certain value that's right there. Right. So what I kind of want to do is a similar thing that we did with our carrying capacity, but like the opposite. So I'm going to make some statements here. When we introduced this n term, what we wanted to be negative in rate of change if our population was above it. We want dt to be negative if p is greater than n, and dp dt to be positive if p was less than n. And what that led us to produce was this factor of 1 minus p. Ooh, not a plus, that's important. Not a plus. 1 minus p over n. Right? For m, we want the opposite. We want dp dt to be positive if our population is above the minimum viable population, then we should grow. And we want dp dt to be, whoa, that didn't make any sense right there. I mashed together a whole bunch of things right there. dp dt to be positive if p is less than n. Here we want it to be negative if p is less than m, right? If our population size is below the minimum viable population, then their change in population over time should be negative right there. So notice that these sentences are almost identical to each other. We've just flipped the positives and negatives that we want, and therefore I'm going to build a factor that looks exactly like this, but I'm going to flip its sign. And to do that, all I can do is just flip these terms. So that's going to introduce the appropriate positiveness, negativeness to go along with that right here. So that's what I think I want to throw in as my something term right there, is a term that will have the appropriate positives, negatives, depending on whether we're bigger than it or smaller than it over time, right? So let's define this thing now to be kp times 1 minus p over n times p over m minus 1. What you should notice is that this is a cubic. P times p times p. It's a cubic, right? So I know what cubic graphs look like. I know how to find roots of factored cubic forms. I think we're in really good shape to identify a bunch of behavior about this, or in a sense, maybe use these graphs to validate that this is actually giving us the behavior that we actually wanted. So for A, for our phase line here, where are our equilibria at? Well, I can see our equilibria easily by setting this equal to 0. dp dt equals 0. That tells me I'm going to see that p equals 0 is one of them. I can see that if p is equal to n, then 1 minus 1 is 0, so everything goes to 0. So p equals n is one of them. And I can also see that if p is equal to m, then we get 1 minus 1 is 0, and the whole thing goes to 0. So it seems like these are my 3 equilibrium locations. So it seems like I can go ahead and draw my vertical line, and remember that this line is the p-axis right there. I'm going to label on it my 3 points of interest. I know that I don't need to talk about populations below 0. Ooh, I don't want to fill in that circle. I don't know what's happening at that circle yet. There's my first equilibrium of p equals 0. We get a p equals m and a p equals n right there. Right? So for my phase line, I know that as the p's get bigger, we're going to go from 0 population to our minimum viable population to our carrying capacity and beyond out there. All of our possible initial conditions have been met now. Right? So here's some things I'm seeing. If our population is between 0 and the minimum viable population, what we're expecting is that this should be going down right here. This is where we should be saying there's not enough of you to survive as a population over time. And notice if we pick a value like m over 2, then we're going to get positive. We're going to get from this guy, we're going to get more positive stuff because it's 1 minus a small fraction. But over here, we're going to get negative stuff because m over 2 over m is 1/2 minus 1 is negative 1/2. And that's giving us the positive, positive, negative for that guy right there. So I'm going to say here that we get positive times negative from our g of p. And that tells me we're pointing down here. So what I'm seeing here is all surrounding things near p of 0 point towards it because there's really only stuff on one side because we're talking about populations. So I feel comfortable filling that in and saying that p equals 0 is a sink to me here. P equals m is an equilibrium. I want to see what's happening between m and n. So let's again play this sign game with g of p. If we're plugging in a positive p-value between m and n, I'm clearly getting a positive for my first group because k times p is positive. If we're between m and n, then that means that we're smaller than n. So that means 1 minus a fraction is going to be positive. but we're also bigger than m. So we're going to get a number bigger than 1 minus 1, which is also positive. So it looks like this is positive times positive times positive. So we're going to get a positive rate of change of population, and this is going to grow between those two right there. Finally, I can see that if my population is larger than n, that we can again play the same game right here. We're contributing a positive population with a positive k, so that's positive. If p is bigger than n, then now this fraction is bigger than 1. And so 1 minus a number bigger than 1 is now negative. But over here, if our population is bigger than m, then that means a number bigger than m over m. This is bigger than 1 minus 1, so this is still positive. But overall, when you multiply a positive times a positive, we get negative stuff, which is exactly what we expected. If you're above your carrying capacity, you should decay down to it. So I'm seeing here that it seems like our carrying capacity at n is stable, right? If you're at your carrying capacity and I bang on the table, right, I either kill 20 African white rhinos or I magically bring in 20 more, then it should move back towards that stable equilibrium of the carrying capacity over time. On the other hand, if you have exactly your minimum viable population out here as your population size, then all I have to do is kill one African white rhino and the species is guaranteed to go extinct, drop down to 0. On the other hand, if I magically introduce one new African white rhino to the circumstance right there, then we now have more than our minimum viable population, and we will expect that population to grow over time to its carrying capacity once again, right? So it looks like P equals M and P equals N, our minimum viable population and our carrying capacity, are both equilibrious solutions, are both equilibrial locations for the population size, but one of them is a stable one, the carrying capacity. One of them is an unstable one. We're going to talk about some really exciting things about when these two move in our next section when we talk about bifurcations coming up in our next section right here. So we actually still have quite a bit more to say about these two and what risks we have associated with biological populations. What forces, so when we exert human forces on populations, how does it influence where these two things are? That's my question to you. What do human pressures do to the locations of P equals M and P equals N on this graph? That's one of the questions that we want to be able to answer later. It's going to be a little bit in section 1.7, but a little bit more things coming in the future here. So the question is, can we only say things surpass equilibrium solutions in situations like this? So one thing that's, according to our model, we will never cross an equilibrium solution. The reason that we know that's not exactly correct associated to biological populations is because biological populations aren't continuous. They're technically discrete, right? You can't have 14 and a half African white rhinos out there, right? So the problem with this model relative to the real world description is that technically populations are discrete, but we're describing it with a continuous cubic model. I think that's a really good idea because the broad strokes of our model do agree with the population stuff overall. But obviously it's the case that like all it takes is like having one additional African white rhino and now we're like above or below an equilibrium that we may not have been before. So we have to sort of think of a continuous analog associated with our populations, which technically isn't the case. Populations are discrete, right? So that's a little bit of where this disjoint occurs between the complexity of our model and the validity of its real world application out there, is that this is just a model. It is not a perfect descriptor of what's happening with populations, but it is getting all the broad strokes correct with what we expect to happen with the populations in the long run right there. To further answer your question, I'm going to answer part A or parts B and C right now with some graphs, and we'll kind of see what else I mean when I introduce another dimension to this right here. Right? So for part B, we're being asked to graph P versus G of P. And so stop and really think about what this actually means for us right here. What this really means to me is this is really like me saying this is like our x term and this is like our y term. This is really like me saying graph the equation y equals kx times 1 minus x over n times times x over m minus 1. This is just a cubic. This is all that we're really being able to ask to graph right here. Part B is a college algebra question right here. And I can do this one. I know that our P versus G of P, which is our dp dt graph, right? What this is going to look like here is I know that I'm going to get roots at 0, n, and m, and I know that n and m are positive because they're population counts. So roots at 0, n, and m right there. I also know, let's see here, this is positive p times negative p times positive p. So this is sort of like a negative p cubed graph. So what I know is that this is going to do our decaying over time, right? That we should be experiencing our end behavior that looks like this because it was a negative cubic right there. And I knew what my 3 roots were going to be. So notice that this graph right here, again, is telling us what's going on exactly with this phase line. This phase line can be seen right here. We're going sinking towards this, sourcing out of the minimum viable, and sinking towards our carrying capacity right here. I can see that we're above, so we're moving to the right. We're below, so we're moving to the left. We're above, so we're moving to the right. We're below, so we're moving to the left. My phase line is the p-axis. It is just a p-axis. It's just that this is typically the most useful part of this for us. And again, remember that I just drew a continuous curve, but we're really talking about discrete populations here. So there is, in a sense, a bit of a smoothing out that I'm doing here, a bit of a hand wave where I'm saying, this curve is approximately how populations change. But technically, this should be like a ton of like infinite little like step sizes right there instead of a continuous graph, right? Finally, our graph over here, our graph of t of p, this graph suggests that you know the equation p, but we don't because we have not solved this equation. And boy, do I not want to do it, because to do that would be to do separation of variables. We would have to do a partial fraction decomposition with 3 partial fractions in there, then get 3 different natural log expressions and mash them all together. Nah, I don't want to do that right now. I just still want to get solutions to this thing though. So I am going to graph. I know I only care about a first quadrant here because I only care about forwards time and I only care about positive populations out there. I know that p equals 0 is an equilibrium solution to an autonomous differential equation, so that's a horizontal line. I know that p equals m is also a equilibrium solution, so it's also a horizontal line. And I know that p equals n is also an equilibrium solution, so it's also a horizontal line, right? Well, I can see what's going to happen to my solution curves. Yeah, exactly. We don't want to do this. So, and again, I can do the calculus. I can solve that equation for p, but why? What am I gaining by doing that? If I can draw every single solution curve, then what have I really done? I could technically answer very specific questions like, if I started with a p-value of 7 and the carrying capacity was 12 and the minimum viable was 2 and the k value was 4, then how long will it take me until my population reaches 6? If I had like a ton of detail, then it might matter that I could solve this thing, but it doesn't help me do anything according to the broad strokes and the big generalizations that we might want to make here. So all I'm trying to say here is, according to what we set up with our existence and uniqueness statements last week, we know that none of our solutions will ever cross each other. This is a cubic, and therefore the derivative of it is also continuous, just like a cubic is continuous, so we'll never get crossing of solutions. I expect that any solution starting at time 0 that's below the minimum viable population should decay down to 0 over time. I expect that this one will just remain at p equals m for all time. I expect that any population that starts above the minimum viable but below the carrying capacity should grow to its carrying capacity over time. I expect that anything above the carrying, if we start at the carrying capacity according to our model, we'll just stay there. And if we start above the carrying capacity, I expect to decay down towards it over time. Notice that this is just the 2D analog of our 1D phase line that we just drew right there, right? This is nice. These are 3 different graphs that are all describing the same type of information. All 3 of them are allowing us to do qualitative analysis that requires us to do no more math than what you learned in college algebra. This is literally like find roots to a cubic and you know everything about a complicated differential equation, right? So the point here is we want to be able to do qualitative analysis because in so many differential equations, we can't solve them. This one I just don't want to, but I could. Later, we're going to get ones that we just straight up can't. So we'll have to do our analysis this way rather than try and find some other mechanism by which to solve these things. I do want to go and pop over into our grapher real quick, and then I kind of think I just for the sake of time, I'm just going to talk about one of our fringe examples right here. But that's okay. I think you'll see kind of our good example here. So I'm going to throw in some like numbers into this thing so that we can see some a sort of like a possible case here. So my K value, I don't know. I'm just going to pick 0.05. If that doesn't work out to be nicely visual for us, we'll change it. X is my P value here. We're going to get 1 minus our P value, which is X, over our carrying capacity. So let's say our carrying capacity is like 8 million. We're talking in the millions here, right? So that's our 8. We also want to talk about X divided by our minimum viable. Well, maybe our minimum viable population is like 1 million or something like that, minus 1. Then we should be getting a graph where so I want to get rid of these curves right here. Now, this doesn't really look like what we were doing right here, but I think that that's because my graph's only going up to population sizes of 1. I know that I want to see population sizes as big as 8 million right here for me to see this. So I'm going to change the bounds here. I'm going to make my populations, my Y stuff. Oh, wait a second. I did this wrong. I made these T's. These should be Y's because Y is like our population. T is like our, X is like our T is like our time. Okay. Now I'm going to make this go from our population going from like 0 to 10. And let's see what happens from a time of like 0 to like 10 right here. And when I do this, what we should be able to see is populations bigger or between the two will, oh man, I want to go further than this. I want to go like way further than that. There we go. I think that's a little bit more helpful for me to see here. In fact, let's pull this back for time a little bit as well right there. So what I can see now is solutions above tend down to their carrying capacity. Man, it's really not the number of segments I want. That's interesting that it's struggling to keep going here. So it looks like what's happening, by the way, notice a special thing that's happening. When I click right here, notice where my mouse is. It looks like it progressed in backwards time by some amount and forwards time by some amount. And it seems like the computation that was happening stopped after it went X number of steps forwards and X number of steps backwards. When we go to make our own solution graphers, we want to be able to manually adjust for that. I was looking around for an adjustment where I could say, we'll make the compute more length to that out there. Apparently, I don't know that that's a preset that I can adjust right here. It doesn't seem like it. Oh, those are preset scenarios, not... Anyway, we want to be able to adjust for that, but at least out here I can like kind of get all of my idea by clicking on lots of these things. And the bottom line being, we can see where these equilibrium solutions are. We can see where our growth is happening. We can see where our decay is happening. We can see that between 0 and 1, between 0 and 1 we're decaying. Between 1 and 8 we're growing. Above 8 we're decaying out there. So it does look like our technological solutions are agreeing with our by hand solutions right there. So what H is going to do is H, oh wait, what, am I thinking about H wrong? No, I'm thinking about H right. Thank you for that. So what H is doing is the same thing that you know that it does from the first weeks of Calc 1. H is like our delta X. It's saying how long is one step. I just made the width of one step 10 times longer. So what the risk is, it's going to increase the length of the solution shown. But what I can tell you is that if we make H too big, then our solution is going to look like a bunch of straight line pieces taped together. It's going to lose its smoothness out there. So making H small will make these curves smooth, but we need to do more H's. So the thing that's still happening here is it's still saying only do like 100 H steps forwards and backwards. By making H bigger, it went for longer, but it's got less fineness out there. If I were to make H like 0.5, that's still not doing right here. In any event, again, we're going to play around with all these presets when we're custom writing them, and we'll get to see all that action right there. Great call, though, suggesting that H setting. And yeah, you guys should be screwing around with all your settings all the time out here. Thank you for that suggestion right there. And again, we will build this ourselves, and we'll play around with exactly that parameter and our own built things to see what that action is going to look like there. Cool. So let's go ahead and look at just one of our fringe cases here, just some weird things that can happen, and then we'll call it a day because I know that we're kind of a little bit long right here. And I kind of want to look at this second one right here. The reason why this fringe case, this weird behavior case right here is a little bit weird is because so far everything that we've done today is the first thing we've said is we've said, okay, this is autonomous, there's no t. But notice that if I set dy dt equal to 0, there are no equilibrium. Right? There's no value that you could plug in for y that's actually going to cause anything to transition here, or to cause us to be equal to 0. Right? So there's no equilibrium associated with this guy right here. But we do know that the location of y equals 1 is, in a sense, a special location associated with this guy right here. Because notice that at y equals 1, dy dt is undefined. I know that graphically speaking, just think about this in terms of algebra class, I know to expect a vertical asymptote at y equals 1, which is kind of a red flag to me for real world modeling type things, right? So a thing that I think is kind of worth considering here is notice that if y is less than 1, what types of things are going to happen? If y is less than 1, then I'm getting things like y equals 0, and therefore I'm going to see things like 1 over 1, and so dy dt is positive. On the other hand, if y is greater than 1, then that's going to be things like 2. 1 over 1 minus 2 is 1 over negative 1. That means that we're going to be getting some dy dt that's less than 0 right here. So the thing that's weird about this one is this. It does seem like we're experiencing a change in direction of growth when we cross over this transition value of y equals 1. But y equals 1 is not an equilibrium, right? We've seen stuff that looks like this before, but this usually happened from when an equilibrium was occurring. But we don't have an equilibrium here, right? So what I think I can do is I think I can draw sort of a phase line that goes with this guy. Right? If y is less than 1, then we get bigger. If y is greater than 1, we get smaller. That's kind of what we just learned from doing some very, very quick algebra here. But y equals 1 is not an equilibrium. And I know it's not because you can't say to me that if y is 1, then we have no change. To compute the change, to plug in y equals 1 causes us to have an undefined quantity for our rate of change that's right there. So the kind of thing that's weird here is it seems like things do move towards y equals 1, but then when they get there, there's nothing there, which is a little bit strange to me, right? It's sort of like we are going to approach y equals 1 and then just kind of poof away. So kind of notice that what's happening here is that if I do things like y equals 0.5, y equals 0.9, y equals 0.99, y equals 0.9999, then we're getting things like dy dt. Well, in this case right here, if our y value starts out at 0.5, then I'm getting 1 over 1 minus 0.5. That's 1 over a half, which is 2. If I instead make y 0.9, then it's 1 over 0.1, which is 10. If I make it 0.99, then it's going to be 1 over 0.01. Oh my gosh, I can't write and talk at the same time. That's 100. All right, so we're kind of noticing here that the closer and closer y gets to 1, the quicker and quicker our function is actually growing towards 1, right? It's below 1 and growing towards 1 at a more and more rapid rate. So it's not just that it's below 1 and getting towards 1, it is rapidly accelerating towards 1. And the closer to 1 it gets, the faster it moves towards 1. Right? So it looks like what we're seeing here is that we're approaching y equals 1 in sort of like finite time. We're actually getting there, and then we're poofing away. right? So what we're going to see is we're going to end up seeing a graph that's got like, we've got this kind of weird behavior happening at y equals 1 where we are undefined right here. My ty graph. It seems like things are accelerating towards 1 from below. So it's not just that they're moving towards them, it's that we're accelerating down into this thing, right? And similarly here, if we're below it, we're like accelerating up into it, and then we're just poofing away. Right? So the odd thing here is that we're getting to y equals 1 in finite time, but then the solution does not exist once we actually get there, which is really weird, right? That's an undefined asymptote right here. I should say asymptote, not equilibrium. Right? And this is really odd right here. And again, the good question a student should ask then is, well, what type of real world scenario does this describe? And the answer is probably not any. And therefore, if you are building a model and it has this type of behavior, you should immediately say to yourself, well, I don't know if that makes sense for in finite time for us to actually converge on a value that then doesn't exist right here. And again, if you feel weirded out by some of these things, we can always go pop over, and was this 1 over 1 minus y, and just take a look at this thing in our graph over here, which is kind of a thing that you guys should basically be doing all the time. 1 over 1 minus y. I don't even want to know what's going on right there. I kind of want to reset this guy right here to be back to our like negative 2 to 2, negative 2 to 2. And the weird thing that we can see is, now, here I'm getting the action that I was explaining a second ago. If we make our step size too big, then what we're going to realize that these curves that they're drawing are actually just line segments stuck together. When those line segments are short enough, it visually looks like a curve to you. I want to make this h be a small h again, so that I get smooth curves again. Oh man, it's struggling with the weirdness of what's happening, right? Oh my goodness gracious right here. So we're just breaking this instead. That's highly satisfying right here. Turning on switching seems to fix this. And where am I turning on switching? Oh, switching. Oh, there we go right here. So now the weird thing is still, why are we crossing over that one right here? Now this is still going to be, oh man. So here's, I'm going to explain to you why we're getting wrong graphs from this as our conclusion for today. What I'm going to tell you that I am confident of is that this is wrong. What it's graphing for us is wrong right here, and here's why. What it's doing to produce these curves is it is sitting at a point. It's asking, what direction should we move from this point? And you should notice all it's doing is following the guidance of the little piece of slope line that's right there. So it's going to say, move in the direction that the slope line says for a small period of time. That's what h is right there. It's for how long we should move in that one direction. Then once we get to that new location, we're going to then consider the slope line at that point, which what we have just learned are getting steeper and steeper and steeper and steeper. Right? So what's going to happen here is as we get really close to y equals 1, it's going to tell us that like, oh look, our slope is like 1 billion. So it's going to move a slope of 1 billion for a very small period of time. But what's always happening numerically here, it is accidentally jumping over that y equals 0 value because it is connecting some dots right here. And it's always going to be the case that one dot is going to suggest that we should make a motion that's jumping over that undefined line at y equals 1 right there, producing what is I know to be a wrong graph right there. And so this is very, very cool. I didn't even realize this was going to happen right here. Because this is doing like a connect the dotting pattern right here, it's not perfectly landing on a y equals 1 value for a dot. And so it is jumping over our undefined curve to suggest that our curves are actually going to continue existing on the other side, when in reality, if this is truly a continuous function, which it is, it would hit that y, or it would hit the y equals 1 and just stop existing right there. There would be nothing else to build off of once it gets to the y equals 1. Yeah, I think what the switching does is reverses the direction at which this the at which the stepper functions, which is why when we have it off, it gets stuck oscillating at the non-existent slope for the rest of t. Yeah, and again, we're gonna in a sense fix this concept when we write our own version of this. So this is a great example though of when we're gonna get numerical error, because every time we do something numerically, we need to do a step-by-step process that's attempting to mimic a continuous curve. And when we try and just think about a continuous curve as being a connection between a bunch of points, we might have connected a line between 2 points that shouldn't have necessarily connected or had that behavior between those 2 points right there. It would normally interpret it as a negative slope and then move itself back down, right? So maybe the switching is in a sense like absolute valuing or something like that. But again, the point is just to say, we always still have to think. Don't just blindly believe whatever your graphs are giving us right here. We still need to be able to say, well, if the y value increases and it's a continuous function, then it must have gotten to y equals -1. But since our function doesn't exist at y equals -1, it doesn't make sense for it to just continue growing through it right there. So a little bit of weird behavior that we're seeing out here. So I think that my really crappy graph where all these things look like this is actually a little bit more accurate right here, and that we are accelerating rapidly toward the y value of 1 over time, getting there in finite time, but then poofing out of existence once we get there, because we no longer have a defined y value to describe how y is changing any further once we've gotten there. So a very strange fringe case right here. I don't think there's any great real world model that's associated with this, but that's a good thing for us, not a bad thing. That says that if you build models that have these parts, if you build models that have this behavior, it's probably going to do a bad job of describing to you the scenario that you're attempting to use to mimic it with right there. So this is maybe just our one word of caution for today. We don't just get infinite free easy graphs all the time. And recognize that I could still say to you, tell me what's going on with this phase line. It's not necessarily the case that you're going to say, oh, well, it looks like it's got an equilibrium at 1. We kind of technically don't know that. We're undefined at 1 at this equation right here. So this is just to say, this is like your cautionary tale to end the day right here, is just to say things don't always work out super nice and perfectly. We're not always even going to trust our technology graphs or our hand-drawn phase lines right here. But for the most part, we will be able to in a lot of our real-world modeling scenarios. And why are we getting those issues in our technology? We're going to solve that problem when we get to it in our technology unit coming up here very soon. So a little bit long here today, but we went through some really good examples. These graphs are going to follow us all semester, so they really do matter. Those of you guys that have been in chat helping me out, keeping me on my toes here, thank you very much with that. By the way, I have been misstating what we're doing next. It's section 1.8. That's our next analytic solving technique for linear differential equations. We're still going to hit bifurcations tomorrow, which is, man, if you got depressed about our endling conversation today, then I'm going to make you even more depressed when you watch our next video and we talk about population die-off. We're going to hit that with bifurcations in our next video. I'm going to remain talking about it with a positive voice, even though it's going to be a biologically depressing topic. At least with physics, it's just a regular thing that happens instead of a sad thing that happens in talking about extinctions. But the point is, bifurcations are talking about when do we experience big change in the type of behavior that we see with our solutions. Super, super important application stuff associated with bifurcations. It's also something that's going to follow us all semester when we get into our two-dimensional differential equations. So really good topic tomorrow for bifurcations. Next week, we will get our linear differential equations in section 1.8. So I will see you guys for bifurcations in the next video. Hey, friend the cat, thank you very much. Glad to have you guys here. See you guys next time.